Hello everyone, welcome to the third lecture of the NPTEL course Machine Learning for Core Engineering Disciplines. In the last two lectures, we learned about an introduction to machine learning and artificial intelligence, and we learned that machine learning can be broadly of three types: supervised learning, unsupervised learning and reinforcement learning. We also saw some examples of how AI and ML can be useful in various core engineering disciplines. And the other thing that we learned was that to use AI and ML tools and deploy them, there are three mathematical foundations that are needed. These are probability and statistics, linear algebra and multivariate optimization. In today's lecture, we will start with probability and statistics and build our knowledge in this fundamental area. So, let us get started. So, our topic for today is probability and statistics, right. I will try to go slowly over the topics so that you can understand what is being covered. However, some basic knowledge of probability and statistics, if you already have, this will act as a refresher for you, right. So, like I said, AI and ML, right, they involve the use of large amounts of data. Right, and therefore, to understand and analyze this data, we need probability and statistics. Okay. So, that is the motivation for what we will be doing, and we will be starting with the two broad classification of statistics. So, if you look at statistics, there are two broad ways of looking at it. One is called frequentist statistics, and one is called Bayesian statistics. Named after the mathematician Bayes, right. Now, frequentist statistics may be the type of statistics that you are most familiar with, and in frequentist statistics, probabilities are evaluated based on data collected regarding a certain hypothesis or event, right. So, you define an event and then you start thinking about what are the probability of that event happening, right, and this may involve some form of enumeration. You will try to enumerate the various possibilities that can occur, and then you will look at what are the possibilities that lead to your hypothesis or your event occurring, and then you can write down the probability, right. So, that is how frequentist statistics works, right. However, if you look at its counterpart, which is Bayesian statistics, here probabilities are evaluated from two perspectives. And these are prior to knowing a piece of evidence and posterior to it after knowing that piece of evidence. Okay. So, you can clearly see the difference between frequentist and Bayesian statistics. In the former type, frequentist statistics, we just focus on the event and look at what is the chance that it will occur. However, in Bayesian statistics, we start thinking more broadly. We see what are the things that can influence this event, and then we examine a piece of evidence and we say, look, this is the probability of the event if we did not know about the evidence, and this is the probability if we knew that that evidence was true, and we will see some simple examples of what this means, right. So, let us move on. Okay. So, now we come to the second point regarding frequentist statistics, and which is that no importance is given to other events which may or may not influence the event under consideration. Okay. So, that is about frequentist statistics, and if you look at Bayesian statistics, this is based on the celebrated Bayes theorem in probability, which you would have come across, right. So, the Bayes theorem talks about conditional probabilities, the probability of an event occurring conditional to another event already having occurred, right. So, given these broad definitions, we will now delve slightly deeper into both kinds of statistics, and particularly Bayesian statistics plays a lot of importance in machine learning, because once you know the data, right, once you have a data, you can make informed decisions about it, right, and Bayes theorem and Bayesian statistics plays a very important role in how you deal with your data in a meaningful manner. Okay. So, let us go ahead now, right. So, in frequentist statistics, given an event A, the probability of the event occurring which is denoted as P of A is determined by repeatedly conducting a relevant experiment and noting down its outcome in each case, right. So, then P of A, the probability of event A, can be defined as the number of times the event occurred divided by the number of times the experiment was conducted, right. So, N of A denotes the number of times the event A occurred, and n of omega represents the number of times the experiment was conducted. Okay. And this omega is referred to as the sample space, which is basically the set of possible outcomes, right. So, that is called the sample space. So, sometimes n of omega, which is also called the size of the sample space. Okay. So, now this is what happens in Bayesian in frequentist statistics, and let us take a simple example to illustrate this, right. So, simple example is that a coin is tossed 50 times and a head is obtained 24 times, right. So, then the probability of head occurring, right, that is the number of times heads was obtained by the total number of times the experiment was conducted, right. So, that is 12 divided by 25. However, if you want to look at it in terms of the ideal probability, right. So, then the ideal probability, what this would tend to, if you did the experiment several number of times, right, hundreds of times, is actually the number of times heads can occur divided by the size of the sample space. So, the size of the sample space is 2, because the only possibilities are heads or tails. So, that is the sample space, and we know that number of times heads can occur out of this set is 1, and the size of the sample space is 2, right. So, the ideal probability of getting a head is half, and then if you do an experiment, right, you may find that it is not exactly half, it is slightly lower than half or more than half, right. If it is around that value, then the coin is still fair. However, if it is way too off from half, then probably the coin is loaded, it is a biased coin, right. So, these are the ways in which you can think about frequentist statistics, right. Now, we move on to Bayesian statistics, right. So, Bayesian statistics, right. So, this form of statistics is based on the concept of conditional probability. Which provides a way to account for probabilities before, that is prior to and after posterior to knowing a piece of evidence. Okay. So, now we have to define what conditional probability means, and conditional probability gives you a way to account for finding the probability of an event given that another event has already occurred, right. So, given two events A and B, the conditional probability of event A occurring provided event B has occurred is P of A given B is equal to P of P given A, P of A by P of B, right, and this is nothing but a statement of Bayes' theorem, right. So, now there are certain specific names which are given to terms which occur in Bayes' theorem, right, when we deal with Bayesian statistics. PA is known as the prior probability, right. So, which is the probability of event A occurring prior to knowing whether event B has occurred or not. Okay. So, in other words, your event A is treated as a proposition, like a proposal, right. It is a hypothesis whose likelihood is being estimated given some evidence represented by event B, right. So, event B is treated as an evidential event, right, and we are trying to estimate the probability of event A without knowing whether event B has occurred or not, right. So, that is the prior probability. Now, P of B therefore becomes the probability of the evidence represented by the evidential event B, right. So, P of B is the evidential probability T, which is the probability of the evidential event B or the evidence B, right. So, that is the evidential probability. Now, what are the other terms in Bayes theorem, right? We have already looked at P of A, we have looked at P of B. Now, the terms which are left, these are the conditional probabilities that we have not discussed. We have not yet discussed, right, what is the meaning of P A given B, although we know that it is the probability of event A given event B has occurred, and we need to discuss what is P of B given A, right. There are certain names which are given to these terms within the framework of Bayes theorem, and that is what we will discuss next, right. So, moving on, P of A given B is called the posterior probability. Why? Because it is the probability of event A knowing that the evidential event B has already occurred, right. So, it is posterior to knowing the piece of evidence B. So, P of A given B is the probability of the hypothesis or proposition A right post the occurrence, after knowing the occurrence of the evidential event P. Okay. So, that is the posterior probability. Okay. So, we have now discussed prior probability and the probability of the evidential function, right, and what is now left is probability of B given A, right. So, let us discuss that. So, the probability of B given A, that is given the name likelihood function. Okay. So, this is how likely the evidence B is given that proposition A has occurred. Okay. So, that is the likelihood function, right. So, if we go back to the equation for Bayes theorem, so that is probability of A given B is probability of B given A times P of A divided by probability of B. Okay. So, now using the names that we defined above, what is this called? This is the posterior probability. This is the likelihood function. P of A is the prior probability without knowing whether the evidence B has occurred or not. This is the prior probability, right. And finally, we know that this P of B is the evidential probability. Okay. So, if we write this in words, we can say that the posterior is equal to the likelihood times the prior divided by the evidence, right. And you can use this equation to find any of the probabilities. You can find the prior probability if you know what the posterior is, what the likelihood and what the evidence is, and so on and so forth for each of the probabilities involved in Bayes theorem, right. Now the proof of Bayes theorem, right, the way it is written here is quite straightforward, right. It can be very easily shown, and the way to do that is to recognize that the probability of A intersection B, which is the probability of both A and B occurring, right, is equal to the probability of B intersection A, right. The order of writing it does not matter. Now the probability of A and B occurring is the probability of A times the probability of B, given that A has already occurred, and then if you want to write the right hand side, that is the probability of B multiplied by the probability of A given that B now has already occurred. And from here you can clearly see that this probability of A given B, which is what we wrote as Bayes theorem, is simply P of A times P of B given A divided by P of B, right. So these two forms are equivalent, right. So the posterior probability, which is the probability after knowing a piece of evidence, is the likelihood times the prior probability divided by the evidential probability, right. Now this is if there is just one possibility that can occur. You can consider multiple events, right, multiple evidential cases, and then the Bayes theorem will change slightly. So let us look at how this happens. Okay. So we want to consider the application of Bayes theorem to multiple events. Okay. So if there are several mutually exclusive, that is they are non overlapping, and exhaustive, that is they cover all the possibilities AI that can occur following the evidential event P, then probability of the evidence B is sum over all the possibilities AJ intersection B, right, and this can be written as probability of AJ multiplied by probability of B given AJ, right. And now we can write that probability of AI given B is probability of AI times probability of B given AI divided by probability of B, right. This is the statement of Bayes theorem, right. This is essentially just Bayes theorem. This will be equal to probability of AI, probability of B given AI, and then we just replace the equation for PB that we derived above, that is sum over J P of AJ times P of B given Aj, right. So, this is the way to apply Bayes theorem if there are multiple events Ai that can occur given the evidential event P, and then you can find the probability of each of the hypotheses Ai and proceed from there, right. So, what we will do is we will end this lecture here, right. In today's lecture we looked at Bayes theorem, right, the Bayesian approach to statistics as well as the frequentist approach to statistics. These are the two classes of statistics that are common, and in AI and ML, because of the availability of lots of data, you can examine various hypotheses, right, and therefore the Bayesian approach to statistics becomes very important, and that is why we have spent a lecture learning this. In the next class what we will do is we will take an example about Bayes theorem just to solidify our understanding, and then from there we will move on to understanding continuous and discrete probability distributions, because these probability distributions will later play an important role in understanding how well ML models are performing, right, and how we can do an error analysis of these ML models, right. So, thank you for joining in, and I will see you in the next lecture.